Am I too loud? Am I not loud enough? How's that? Is that pretty good? That's pretty good. Okay. How you guys doing? My name is Frank Evans. I am a data scientist with Exaptive. I don't know if you happen to know, we're a data science company over in Midtown. Cool building with all the containers, all the shipping containers as our building's made out of, so feel free to stop by and say hi. I'm going to talk to you guys a little bit about Scikit-Learn, about machine learning a little bit in general, and specifically about doing machine learning in Python with a very popular library called Scikit-Learn. So we're just going to jump right in. I'll get a couple of slide sort of things here to show, and then we'll do a little bit of live demo and see if we can't get that to go wrong also. Okay. So 4 things I want to talk about. Machine learning in general, we're just going to kind of scrape right over the very top of that. So if you are an analyst in probably any capacity, this is going to be boring to you. Feel free to get another slice of pizza. If you're not really an analyst, you're a programmer, an engineer in some other capacity, or non-technical in some sort of valent capacity. Hopefully this is sort of the grade that we're sort of looking for. So a little bit of intro to machine learning in a very highly general sense. The Scikit-Learn library in specific, we'll touch on it a touch. The sort of structural approach, the philosophical approach to how you solve machine learning problems using that library, and you'll see why that's very useful. And then we'll get as quickly as we can over to get to demo some fun stuff, some stuff that you can take with you if you want. So machine learning, the way I like to explain machine learning is actually strikingly similar to the way Greg mentioned it as I was walking up here, which is data is huge, people are expensive, and computation is cheap. Computers are dumb, but they're incredibly fast. And so if we can find a way to take advantage of that, because they're incredibly fast, computation is exceedingly cheap. If you could somehow get the amount of power that we have, if you could somehow get a MacBook Pro back to 1941, we could have won World War I in the first 3 months. Like, that's how amazingly fast computers are. And so what machine learning is using applied statistics to let the computers program themselves. So how can we not have to do all this stuff ourselves because it takes us a long time to do it, but how can we create a framework taking advantage of the fact that computers are really fast, use applied statistics to get it. There's a few different types of machine learning. I don't want to jump too deep into this, but it sort of will kind of give you a sense of how to think about a problem. So supervised machine learning is where you've got a set of examples with the right answer for each example, and you want to learn the pattern so that you can get the right answer on other examples where you don't have the pattern. This is the most common type. This is what we're going to look at today. This is the vast majority of problems that are sort of well solved are this way. Unsupervised, so I've got a whole bunch of data, and I want to sort of learn some generalized patterns, but I can't really prove that one of them is right and one is wrong. I just want to try to restrict the sort of level of unknown to something that's a little more manageable. And we can talk a little bit about it. It's a little outside of scope here, but all of this is supported by the library that we're going to look at. And then reinforcement's the third one, and reinforcement's the rarest of the 3. It's kind of an up-and-comer in a way. I want to start with something that I know now, and then as new data sort of comes in live, I want to alter what I know to make decisions. So sort of kind of something that will keep its understanding up to date. So 3 different types. Now we're going to talk entirely about supervised machine learning, and there's kind of 2 different types of it. And they look very fancy, regression and classification. They've got great fancy names. Everybody's got to have their own, token words whenever you're in a specific domain. And in this particular case, it all comes down to what are you trying to predict? Are you trying to predict along a continuous scale, or are you trying to sort of categorize things into groups? So if you're trying to figure out, hey, what should the price of something be? What should the value of something be? What is the probability that something will happen? That's a continuous space. I'm trying to figure out, based on houses, what the housing price should be, et cetera. Based on maybe how big the house is and how many garages and bedrooms it has, et cetera. And a housing price is not really categories. This one may be $100,000, this one may be $100,040. Like it can pretty much vary anywhere. Whereas classification, we're kind of trying to divide things up into groups. So my email wants to know, is this spam or not spam? I want to be able to tell, which flower I'm looking at based on its characteristics, which comes from the data set we're going to use today. So somehow I want to take the data that I have and I want to put it into buckets, put it into categories, sort it in some capacity. Okay. The one thing to keep in mind, we're going to play a little bit with this today, is that we're trying to get to is this idea of generalization instead of memorization. So because computers are very fast, it's extraordinarily easy to kind of just memorize where everything is, and then so as we're taking a look into this, we're going to train on some information, and then we're going to essentially check ourselves by taking some data that we didn't learn from and see if the patterns that we learned will generalize to that very smooth kind of black line that's giving me good information versus that crazy green line, which is technically more accurate, but is probably not really capturing information. And this will make a lot more sense here in just a moment. So let's go into Scikit-Learn itself specifically from maybe a Python perspective, less machine learning in general. Let's go a little bit more Python in general. A whole bunch of things up here, so sorry about that. It's the quickest way to get them all up here. It's open source, so you can go look at everything. You can contribute to it if you want to. You can write documentation for it. They would love that. Completely community built, so it's not materially supported by any one company. There's 10 or 12 companies that do support it, but it's not it's not one of those. It's not like a Bootstrap, which is primarily Twitter, or a Cassandra, which is primarily Facebook type of thing. It's a completely community built, sort of ironically bootstrapped itself up. BSD license, use it for anything you want. So personal projects, commercial projects, hate speech projects, don't do that, but you're allowed to, whatever. You can use it for anything that you want to in any capacity, and the BSD license means that you can sort of build anything on top of it that you want to. They have fantastic documentation, which we may take a look at as we're looking at what they do, but they have incredible documentation with highly visual examples, great use of their internal data sets, walks through exactly how to do things, has a great description of sort of every single object, every single method, every single property, exactly how it works, what data type it expects. It's their documentation style for this grade of a library is very enviable, and in my opinion is a good one to look to for your own use cases. It's primarily numeric. When I say it's primarily numeric, so it's about solving numeric problems, numeric machine learning problems, so kind of like the ones I just talked to you about. Things like regression, so trying to figure out in some sort of discrete area, in some sort of continuous space what a value will be, trying to categorize things into buckets or categories, but primarily based on numeric data. And this is as opposed to maybe things like natural language processing, graph structure processing, some of the more kind of magic black box sort of deep learning-y type of things, image processing, audio processing. It's as opposed to those sort of areas. There's great libraries for all of those things. You guys should have talks about them because they're really interesting. But Scikit-Learn specifically is around numeric data, and in almost every case, somehow you either have kind of a row and column-y sort of thing, or you're going to get to something that is sort of rowish and column-y as a part of what you're doing. It's built on top of NumPy and SciPy. So that's numerical Python, scientific Python. You may or may not be familiar with them. If you aren't, they're fantastic. They're sort of the kind of base level of being able to do numeric operations in a number of different ways, highly efficiently, highly effectively. They really has really been highly optimized down to very low levels on machines to be able to do really hardcore processing things. And this is built on top of that, and most of that functionality you sort of get for free, which is fantastic. We'll see that in the code samples here in a second. And the philosophy, I don't know that they invented it, but the philosophy of Scikit-Learn is very consistent with other machine learning libraries. So if you were to sort of learn how Scikit-Learn works, you wanted to do natural language processing, you went and picked up GenSim or the Natural Language Toolkit, both very highly capable machine learning libraries specifically for language processing. The philosophy is very, very similar around it. Similar if you picked up like a Keystone, you wanted to do some stuff in Spark. And again, the philosophy is very consistent with other fantastic machine learning libraries. So I don't know whether they invented it or not, but it's sort of a good way to get it in your head, and we're going to talk about that next. Components, the things that it does, so supervised and unsupervised learning, all the stuff I just sort of laid out. So tons of different ways to do both of those. Transformation, so taking your data sort of in one format, transforming it to another format that could be useful. There's a lot of good stuff in there. We'll look at a little bit, not a ton, but it is good transformation stuff in there. Evaluation and tuning, so being able to use stuff right out of the package to see like how effective was your model, ways to sort of tune the different knobs, which we'll play with a little bit today. We'll tune some knobs and see what happens. And so different ways of coding and ways to programmatically do evaluation and tuning, and then a lot of great sample and test data sets just to sort of see that your stuff's running end to end, or try out new ideas without having to get some data and make sure you load it and that sort of thing. There's maybe 25 built-in data sets that have a bunch of different properties that are terrific for sort of getting up and learning and not having to go learn a bunch of sort of separate valent things, which is fantastic. So this is more just sort of for the record, if you will. I don't see a ton of like white apples glowing back at me right now, so I don't know how many people really want to try to follow along in any capacity. But I'm going to dump all these stuff up on SlideShare, so if you want to grab them later, you want to try to work through them on your own and then just start modifying it and monkeying with it yourself, please feel free to do it. I would highly recommend, for the vast majority of stuff, run everything in a virtual environment. It'll make your life so much easier. Make your life easier in most things anyway. I see a lot of people nodding like, yes, it will. It will. You're right. You're right. Greg's laughing. He doesn't laugh for nothing. He laughs because it's true. It'll make your life a whole lot easier and pretty easy to do. So just see if you've got virtual env and lying around installed. If you don't, spin one up. I always call mine VE because I'm highly creative. That way I always know where it's at in my folder. And then just source the activate so that it will fire up your virtual environment, and then just pip install NumPy, SciPy, Sklearn, and you're home free. Takes this whole thing from dead scratch, takes 15 seconds, and you're in good shape. So more for the permanent record than for you guys literally today. If you're on Windows, I apologize. Tried this anyway. It might work. This is fake code. This is not a real thing. But I want to talk about the philosophy of how you do things in Scikit-Learn, and then we'll do real code. But I don't want you to get hung up on the specifics of real code until I can throw some fake code at you. So import the module that you want to use, which you'll see in a minute, whatever the module's name is, whatever thing you want to use, it's got a module name. So go grab it, and then you're going to build the model itself. And you're going to build the model itself by just creating the object. So aside from the code for just a moment, you could kind of do a three-step process. You're going to instantiate the blank object, for lack of a better term, and the configured object. You're going to instantiate this instance of an object with all the configurations in place. Then you're going to call a method that says, let me have the data, please, effectively. And it's going to do its thing. And now the state of that object is trained on your data. And then behind that, there's all kinds of methods and properties that you can interrogate that object for. And it will give you things back, whatever sort of contextually appropriate. And it'll give you back like a whole bunch of different type of results, and you can sort of use them as you want to. You can dump them into a database, you can return them to the screen, you can print them out and to look at them, you can use them to as a feedback loop to do tuning, you can dump them all into JSON and put them somewhere, whatever you want to do with them. But that's the idea, the sort of general philosophy. Instantiate a blank object with all your configurations, feed data into it, let it mutate itself, train itself on the data, and then essentially interrogate it with methods and methods and properties to get back what you want. The other thing I'll mention is I said it was built on top of NumPy and SciPy, very heavily NumPy. It's going to, it being sklearn or Scikit-Learn, is going to want in almost every case, in enough cases, just go ahead and think always, and then the documentation will tell you if I'm wrong in a specific example. It is almost always going to want your raw data, your features, as a matrix. Now that can be a two-dimension NumPy array. It can be something that's kind of matrixy like. It can be an actual SciPy matrix. So SciPy has great stuff for having sparse matrices that will like respond as though they are a full dense, I've got all the zeros in here, taking up your memory space matrix. Plays super nicely with pretty much any matrixy looking thing from NumPy or SciPy. So if you can get into there, you're home free. And then if you have labels and anything where you're going to give it the correct answer, if you will, supervised learning, I'm going to tell you, here's the answer for these. It's going to want that, your labels as a vector, so just a one-dimension NumPy array. It might actually take a regular array. It's going to convert it into a NumPy array. You can configure all that stuff, but it's going to convert it into a NumPy array of like 32-bit floats, I believe. Anyway. That's going to convert it all into a NumPy array. You can control it. You can make them 128-bit floats if you want to, but unless you're building space shuttles, don't worry about it. Okay. So let's go actually play with some real code. So I've got my incredibly small screen here. So let's bring this up until Mark says he can read it. Mark, can you read this? Is that big enough that you can kind of, okay. And let's get a classification. So there's an example here. I got tons of stuff all commented out. We're going to sort of walk through this piece by piece, and we're going to look at it sort of the way you would if you were doing your very first. Yeah. Sorry. I meant to have all this commented out, and then I will. Yeah. Okay. Is that somewhere in the neighborhood?
I hate to say this, but black text on a white background would be a lot more legible.
I don't know if I don't, yeah. Anybody have like the 30-second way to make Adam do that? Because I don't. Is that pretty good? Is that all right? Is it good enough? Can we pretend? Get more pizza. Get more, it'll be all right. Echo, hello. Is that? Sort of, we could bring that up a notch. It's not going to hurt anything. Okay. So we're going to walk through what we're going to do over here. So this is a kind of a small machine learning example. We're going to be doing a classification. So I've got some data that I'll describe here in a minute. I'm going to want to learn an answer of some kind, which I'll describe here in a minute. And so I'm going to want to do a classification. I need to put this into some sort of, category, sort. I want to sort these things into separate buckets. Okay. So the first thing I've got is I've got my data here. This is a built-in data set. So I import my stuff here. I import, make sure I got the data sets module. I got the tree module. I kind of give away. We're going to be building a tree of some kind. Model selection, so we're going to play with some of the meta functionality. We'll get to that in a minute. But for the moment, all I really need is these data sets. In fact, I can do one of these things. There we go. And I'm going to be, loading the iris data set, and then we're going to look at a little bit of it and see what it looks like it's going up. So the first thing, let's fire up the virtual environment. I love that it makes that noise.
Apparently audio works.
Audio does work. I just muted my computer. Thank you. Appreciate it. Okay, so we're going to run this, this script and just see what it gives back to us. Okay, so let's give this back a few things. So first of all, I ask it what I want the iris data, so I just go to the data sets and I say, let me have the iris data. And I'm going to split that out in just a moment into its features and its labels. I looked at the documentation. I know what the iris data roughly looks like. And what I get back out of it is this first layer here. So print the type. So I've got a NumPy array and a NumPy array for both of them. So I get that right off the bat. Don't have to deal with that. That's fantastic. I'm going to ask what the shape is of these two objects. So the very first one, these labels, it is 150 records by nothing, which is just telling me it's a single, single dimension. So not different than a list array, whatever you want to call it. Not materially different than a list, except for it's a vector. Don't need to get started on what the difference is. And then my features themselves, I've got 150 records, 150 rows, 4 columns. So it's 2 dimensions. And let's look at a little bit of them. So let's just look at the first 5 of the labels. Looks like they are all 0, and then these are a matrix of some floats. Usually let's look at the last 55. That's a good idea. Let's look at the last 5 and see, are they materially different? Oh, that's everything but the last 5. That's what happens when you don't pay attention. Anyway, but there's all of our data. Okay, 0, 1, 2, 2. Okay, so our labels are these integers, and they don't really seem to be continuous. They're hard integers, 0, 1, 2. That's what's standing in as our different characteristics. So let's go through and build something with them. Now, the first thing I definitely want to do is I don't want to use all of my data. I want to have some sort of way to check to see if I did that. Did I draw that like squiggly green line to memorize everything? And I overfit? Did I, overtune until I didn't have something that was generalizable anymore? Or am I learning something pretty smooth where if I give it examples I didn't learn from, it would do a good job? So to do that, I want to use, again, this is one of the, I think this is part of model selection, isn't it? Yep. So we're going to have to turn that off. So one of the things that Scikit-Learn gives me is just a super simple way to say, take my data, do this train test split it out, randomly split it out where I've got 2 chunks that look exactly the same in sort of their dimensions, and particularly in their width. And it keeps them straight so that if I randomly choose one from the feature, a row from the features, I choose its label. Keep everything straight for me and randomly pull out 25% of it into a different set, and then just a random state, like any other random state. Throw it an integer so that it will always be the same. Okay, then let's look at the shape of that stuff. So now I've got 2 sets. I've got 112 records, still 4 wide. Yeah, I've got 38 records, still 4 wide, and then I've got the vectors of 112 and 38. Same size. Now I've got a set I can go learn stuff from on the 112, and then I'm going to essentially make myself, do a quiz on the 38. 38, you're not allowed to have the answers, not allowed to learn from them. We'll see how good you did. Okay. So we want to keep that, and we're not going to look at that anymore. We want to get the model up here with its initial sort of settings. I've got a bunch of different settings here. We are going to build a classification decision tree. I don't know if anybody happens. You may be familiar with a decision tree? Familiar with the decision tree? Please say yes by just staring at me and doing nothing. Okay, Clint likes it. Okay, yeah, okay. So decision tree is what we're going to build. We may look. There's a fantastic graphic that sort of explains how a decision tree works. Some of you may have seen. If you haven't, you should see it. It's fantastic. It's so good that the people at the bottom, they told like what they plan to do next. And that was like 3 years ago, and they've never done a second one because they've all probably they both probably got offered jobs like that were cost like, paid like 4 times as much as they got, and they just never made the second one. That's how good the first one was. Okay, this was, this is, okay. Anyway, but I'm going to set up several of these things. So there's my random state, 144, choose whatever you want, but I chose 144, doesn't matter why. I've got a criterion of some kind, so I'm going to feed it that, and look up in the documentation, see what that means. The minimum number of samples to split on, I'm going to say 4. Actually, I should change that. But yeah, the minimum number of samples to split. So I have to have, every sort of mark on my decision tree. I need to make sure I have at least 5 samples that match those criteria before I can try to get better at learning. Otherwise, I could just learn all the way down. We'll play with that. The maximum number of features, so that I'm just going to have it do, there's only 4 anyway, so how far could it really go? These are mostly the defaults. I've just sort of hand typed in the defaults so you can see them, and so it's easy for us to sort of monkey with them and see what happens. And then when I get done, I'm going to print what type that model is. So I'm going to see what kind of thing did I end up with. What I ended up with is an sklearn.tree.tree, so a double tree, hotel. Anyway, nobody? Wow. Is the pizza not that good? Is that what's going on? Okay. sklearn.tree.tree, decision tree classifier. So I've got, here's my object. Nothing's really happened to it yet. All I did was I just sort of said, hey, give me a blank one of these so that I can use it for something. And now I'm going to feed in that data. So you remember I split up here to my training and my test data, and I'm going to take my training data and my test data, my training data and my training labels, those 112. And I'm going to feed them in on this model.fit. So I'm not returning anything. I'm just going to let it mutate its internal state. And then when I get it back, it will have all the answers I desperately need to know. And when I get it back, it's still the exact same object. That's all I want to show. That's 100% of what I want to show with that. It's still the exact same object that you put into it. Nothing's changed there. But what I can do with it now is I'm going to feed in my test data. So these are FT, my features from the test data that I split up there above. And you'll see this, I bound all my variables here. This is sort of a personal preference anyway, but also to make it very clear what was what. Capital X and small y standing in for a matrix of features and a vector of labels, sort of mathematic notation left over from mathematic notation. But you'll see that reinforced here, which is nice. If you want to take this to your stats professor or something, he will understand it too, or she. So now I'm going to send something. I'm going to interrogate it. In this case, I'm going to interrogate it by giving it that test data and say, make your predictions on this test data, and just let me see them. So show me what you learned. And now here's my randomly generated test data, and it thinks the first one is a 1, the second one is a 2, and the third one is a 0. What are these things really? I mean, you saw up here somewhere in history, that I've got these 4. So if you happen to be familiar with the IRIS data set, it is a data set from 150 years ago, something like that. But it is measurements on the sepal and petal width and length in centimeters. And based on those 4 things, just knowing the width and the width and length of the sepal and the petal. I don't know what a sepal is. But on a sepal and a petal, can you figure out what flower? I think there's like 3 or 4, 3 different species of flower. And this was from somebody gathered it like in the 1800s. And just sort of easy 150 records, nice easy way to see if your classifiers work and see if you can do something with something toy grade with it. So it said the first one is whatever that flower is, and the second one's whatever that flower is. It's making its assumptions, but really I really want to see is this is test data. I want to run that test. How close to correct did it get? So instead of just asking for the predictions itself, going to pass it in, and I'm going to say, I want you to score, and I want you to score according to, here are the features of the test, make the predictions. It's going to call prediction underneath the hood. And then I want you to compare that against the test labels and see how often did I get it correct. And in this case, I got it correct 94.7% of the time. It's not too bad, all things considered. Like that'll get you an A. But it's very easy for me to tell how accurate I was, where if I want to go change it maybe up here, so let's say instead of optimizing for entropy, I wanted to do it based on Gini. I don't even remember what that stands for. It means something. And I get about the same, don't I? Almost the same. I'm guessing. Let's crank this up. Let's say you got to have 10 before you're allowed to spill. Let's back it off. And I wonder what's going on here. Oh, because of this. Nah, it's because of that. There we go. Sorry, this is being taken over by this. Might set that to none if you want it to auto-select, my fault. Okay, anyway. So yeah, here I've got, if I were to back this off where I'm using this method, and I am telling it to pull itself back where it can only learn in groups of 10. It can't go all the way down to, if it could go all the way down to groups of 2, it can probably learn something that's too specific. Yeah, 94%. But if I were to tune this up to 10, there we go. Now we're up to maybe 97%. So I can sort of see how accurate is my thing according to these different approaches. And I want to be able to go a little further than that. I don't want to not just see only that, although we'll leave the accuracy there. It's good to know. I've got a few other things I can get from it that will just sort of give me some high-level stuff. So this is the number of classes. There's 3 different classes. So I'm guessing amongst 3 different things. Random. If I just randomly guessed, it would be a 33% chance. So the information gain I've got is 97 minus 33, et cetera. 4, so there's 4 different features. You saw the 4 different features: sepal, petal, width, length. Number of outputs is only 1 output, so we're only trying to guess one thing, even though it has 3 classes. So yeah, that's useful to have. Might be useful to know that it's there. I can see the actual tree itself. I have no idea why you can do this, because I think, you have to save your file before you run it again. Good pro tip, kids. It will show me where it's at. Doesn't really seem to be anything you can do with it other than it's an object now. You can reload it. So now you have your trained tree. You could, pickle it off into, B64 encode it, pickle it off into something, dump it off in a database, keep different ones around. You could reload it without having to retrain it. Imagine this took, 20 minutes to train. You could essentially wake it back up from something like pickle in, a second. Or in a few milliseconds instead. So it could be, it's certainly useful that way to have the actual underlying object where you can get your hands on it if you really want to. And then I've got here, I'd like to be able to marry up something a little more friendly. So I've got, sepal. Oh, yeah, okay. So I said I had 4 things and they were the sepal, et cetera, right? Well, which ones are which? Well, the first one's sepal length and the second one's sepal width, the third one petal length, petal width. And then, here's the feature importances. So it might be able to say, sepal width is, had to do, was like 13% important versus, the petal width seemed to be the really important one. It was the determining factor in getting it correct, 77% of the time. It made 77% of the decisions weighted for accuracy. That's nice to know. It might be nice to make it a little more user-friendly. So let's do that. So all I'm going to do is just, I'm going to kind of take advantage of the way that it's going to hand me the 2 of those. I'm going to zip them up together. I'm going to dump them into a Python dictionary. So nothing very revolutionary. Then I'm just going to print the dictionary 1 line at a time so it's easy to read. And so now, maybe my particular project, these are the things I wanted to interrogate out of them. And I wanted to sort of learn how accurately could we predict based on this data rather than literally make predictions. And so now I've effectively got, a JSONable object that I can output from my, maybe wrapper function that I made around this whole thing. And I've walked end to end with taking some data right off of taking some data that they've got in here. We built something with it, spec'd it all the way along the way so that what you're getting at each stage is what you expect to get, kind of mentally makes sense. Except for the 55 thing. Yep, that didn't. But the rest of it did. And then you have just sort of standard Python-y control over how do you want, because you need to interrogate that built object. You can save the object, you can do anything you want to, and wake it back up later if you want to, which is nice. But you can also, interrogate. It's not you can, you have to. You have to interrogate that object back to get whatever you want from it. It's got all kinds of information. Use it to do the thing, get the metadata about it, get the descriptive information of how it works, marry it up with your original data's labels, whatever you want to do with it. The point being is that you're sort of forced into infinite flexibility around that, which is a lot of fun, particularly if you didn't want to use a built-in data set. So let's say you got a CSV or something lying around. So I don't have an end-to-end on this particular one, but it plays wonderfully with Pandas. If you happen to use Pandas. Pandas is like Python, but R, but also Python. So dump Pandas in there as well. I've got some fake data, CSV of fake data, and I'm going to read it and look at what kind of type it is. It's going to be a Pandas data frame. In fact, we can go ahead and do this. So Pandas example. Here we go. So this is some fake data that I made from Mockaroo. I don't know if you haven't used Mockaroo, it's fantastic. It will find things like this particular one. It's for a separate use case. This particular one is real companies, or kind of half fake, faked data around actual companies. And it is it's set to have patterns that can be found through decomposition analysis, but cannot be found through correlative analysis. So it will fake no pattern in correlation, and we've essentially told it that we want it to do that for the purpose of making sure is the thing that we want to do. It's going to be kind of unit testy data, how we're going to make sure that our thing is doing what we want it to do. But we can use it here too. We can use it. I've just got a CSV. I pull it in and it tells me I've got a data frame. I can tell the data frame I would prefer you be a matrix, because you're kind of a matrix anyway. Just sort of wipe your labels off the side and call yourself a matrix, and it will do that. It will make itself into a NumPy ND array, and now that I've got that array, now that I've got that two-dimensional matrix, in fact, here's the first X number of records. It's 100 records, 6 of them. This doesn't have any labels, so that's why I can't feed it into my classifier. This one's more unstructured data, me trying to, you want to find a pattern. In this case, the pattern, ultimately, I hope you're figuring out, is that tech companies make more money given the same amount of expense. That's sort of the pattern that you're supposed to be able to find, but you can't find that in correlation analysis. You have to find it through decomposition, way outside of the scope of this, but the point of this is that if you've got data yourself, no matter what format you've got it in, it's pretty easy with whether it's something that splits your data up like we did up here. So I've got data and I want to sort of use it to train itself. There's also a way of doing it with what's called cross-validation. Anybody familiar with cross-validation? So yeah, okay, awesome. There's a way of doing this exact same thing with cross-validation. So I did a single validation here. I just split it up. Hey, randomly take out 25% and train on 3/4, and then how well did you do on the other fourth? What cross-validation will do, let's say you did it with 4 chunks like that. It will split it randomly into 4 chunks. And then it will say, okay, I'm going to learn from the first 3 and then try it on the fourth. Now I'm going to learn from 2, 3, and I'm going to learn from 1, 2, and 4 and try it on the third. And it will try sort of all the different combinations of those. It will try all the different and test itself and build separate models and then just sort of average amongst those to see how generalizable it is. Given a single state, it will average its capabilities across trying all these different combinations. It's a lot of fun to play with. So that's sort of the coding example part. Everything from getting your data from wherever it happens to be, comes in, load it from a file, get it from a database, whatever. If you can get it into anything sort of rowy and columny, you can pretty easily get it into Scikit-Learn. Do something numerical machine learning-ish with it, and every single, I only showed you one example. I only showed you a decision tree classifier. If I were to show you 10 more classifiers, regressors, clusterers, all of that stuff, they will all look almost indiscernible. The ASCII art, to use your phrase, Greg, the ASCII art will look almost exactly the same. Get the data, split it if I need to run some sort of test on it. Instantiate, shove the data in, and interrogate what I want back out the other end. So let's see, fire this thing back up. Still on, there we go. A couple of quick tips before I sort of open it up where we can all talk. It's super easy to try different settings, which means it's super easy to overfit. So be careful. I mean, you can imagine parameterizing, those five different parameters that I had in there, and then just, for loop till you run into the gutter, and try them all and see which one does the best. And that one's obviously got to be the most generalizable. And so be careful. It's super easy to, like anything with program, it's easy to overdo it. So, buyer beware. Your data needs to be a matrix or a vector in NumPy or SciPy, so plan for that. But there's fantastic ways to get your data that way. If it's anything sort of relatively in the neighborhood, getting it that way is a quick Google search away. Spend time exploring what you can get back to communicate your results. So once you have that object, there's usually 6, 7, 8, 9 things that you can ask for back, like show me the decision path that it took to get there, show me the accuracy, tons of great stuff that it gives you back. So, open up the documentation, just sort of print them all out. When I did this one, I can't swing back, but when I did this one where I asked for those classes and such, I just wanted to sort of explore around, see what it would give me back, and take the ones that I thought were useful, and the importances were maybe useful, making the predictions and the accuracy level was useful. So, spend time playing with that. Make sure your model choice and approach makes intuitive sense. Then once you do that, the programming part is strikingly easy. The programming part is super clear. It's this exact same philosophy in pretty much every use case that you can run across. And they published this, which is fantastic, highly useful, especially when you're starting out, that says, start here. It's literally a decision tree that could tell you should use a decision tree, which you got to think that's great. But this is a cheat sheet of based on what you have. Do you have a ton of samples? Do you not have very many samples? What are you trying to do with it? Are you trying to predict I don't think I have a marker here, but are you trying to predict a category? Are you trying to, yes or no? Are you trying to predict a quantity, yes or no? And it will lead you into whether or not, are you going to end up in the classification or the regression neighborhood, the dimensionality reduction, which is kind of an unsupervised approach, or clustering, which is sort of a different type of unsupervised approach. So the top two clumps there, to give lack of a better term for them, are supervised. I have an answer in some capacity. The bottom two are unsupervised. I don't have an answer. I just want to make it where I can actually wrap my head around this stupid thing. And then you sort of go in there. Do you have a ton of data? Do you not have a ton of data? What types of stuff do you want to do with it? So they have this. This is just published right there on their homepage. It's fantastic. Highly recommend it. Other than that, that's all I've got. Please use this as an opportunity to ask me any questions related or unrelated. And if you want to ask me questions or just say hi or whatever, that's me, Frank D. Evans. I'm on the Techlahoma Slack as Frank D. Evans. I'm also everywhere else as Frank D. Evans. So Twitter, email, LinkedIn, SlideShare. I'll dump these up on SlideShare. That's my SlideShare. I don't know, whatever. MySpace, actually. I haven't checked it in 8 years, but if you want to add me as a friend, I'll put you in my top 8. Yeah. What do you got? You can have some more pizza, yes. Oh.
So I noticed the data was in batches, right? And you're handing it discrete batches. If you wanted to stream, is there any way to stream, or is streaming just a bunch of batches?
So there's sort of plugins that allow you to stream with this. I'm sorry. Oh, yes, I need to repeat the question. That's what you're saying. Yes. So you said your question was that there were discrete batches of data. And so if I wanted to do something that was more like streaming data, what do I need to do with it? There's sort of the way that Scikit-Learn handles that. There's sort of plugins that kind of go on top of it. Scikit-Learn itself does not do any sort of live reinforcement like that. The way that it handles that is it will hold a state, and it can continually, there's like plugins, extra things you put on top of it that will sort of mini batch and mutate its state based on that, based on sort of relearning. It works okay for a few things. It doesn't work great. There's other libraries that use this same philosophy that do a better job of sort of like holding a window where every time you feed it data, and you tell it, I want you to learn, I want you to learn yourself based on the last, 1,000 records or something. You don't have to handle any of that windowing around. You have 126 new ones come in, kick out the old 126, or keep them within a time period. There's other libraries that are much better at doing that, but there's some plugins you can do, some for little things, for small things. If you plan to run this in, not massive amounts of, not huge like Hadoop grade levels of data, Dockerize something like this, and you can run some pretty surprisingly intensive stuff against it, and you'll never notice enough performance hit to worry about it. And it's just so super easy to do that you may as well do it that way and go put your thoughts on other things. But no, it's a couple mini batch things you can do with it. Nothing great, but there's other ways that do it really well that use some of their underlying functionalities like plugins. So forgot the names of them though. Somebody else? Anybody else? Not very well. I don't think it uses a ton of GPU stuff. You want to warm up your GPUs, go get your hands on TensorFlow, and that will, that's, in fact, you can cook breakfast on your screen before you leave. That's a good way to warm up your GPU. Or what's the other, Cafe, maybe? Cafe, you probably warm up a GPU that way. It doesn't do a lot of, I think there's ways that you can do some of the stuff in GPU. I haven't really done it. Most of this is, it will parallel process for you. You'll see when you can, so a decision tree you really can't effectively, but when you mathematically can parallel process, one of the things you'll have there is like n jobs, and that's like, how many of your cores can I have? And you can tell it, and you can even tell it none, and it will like, I think you can tell it something like, all -1 or something like that, and it will auto-detect, and it'll ask the OS, that sort of thing. It'll do all the smart things that you hope it does. It'll do the parallel processing for you, but all of the use cases that I've seen are all in in like regular, normal, everyday processors. I'll get to both of you, I promise.
So, how do you decide whether to use Scikit-Learn or something like R, statistical program, to deal with some kind of regression problem, which
Yeah. The vast majority of time it's going to, sorry, your question, I'm getting better at this. So your question is, how do you decide when to use Scikit-Learn versus when to use something like R? So R has sort of has two things. You saw me use Pandas for data frames. R has sort of data frame capability right out of the batch. It's the entire reason Wes created Pandas was so that Python would have an R mode. Yeah. And then for the sort of learning library, there is a library that is incredibly similar in R called Caret. That's caret like a diamond, so C-A-R-E-T, Caret. It's incredibly similar and has almost all the same capabilities, all the same mainstream capabilities, 99% the same capabilities as Scikit-Learn, but all written in R. Beyond that, it's 100%, it's almost entirely personal preference. If you want to take something that's going to run on sort of a medium, amount of load, and I think several DevOps people will probably tell you it's a little easier to like Dockerize things that are running on Python than it is R, but it's not bad either way. There's nothing wrong with it. If you're going to do some things in addition to your project that Python is a little better at, just a little cleaner at, hit some APIs, interact with databases, R is fine at those things, but it's not really its bread and butter. Python's sort of a first-class capability there. Maybe you'd want to lean, but outside of any normal why should I use Python versus R conversation, there's no compelling reason specific to this use case. Greg, number 2.
Is this kind of technology appropriate for very small computers that might be on a remote control tank or drone or something low power, low CPU, et cetera?
I don't know. I've never tried that. I would try it for sure. It's the first thing. Yeah, you got a Pi or an Arduino or something lying around. So I'm so bad at not repeating the question. Is this good for very small computers, like one that's going to run a small tank? A tank's where you went for it, not a thermostat, but a tank. You're gonna drive it around, like have it seek and destroy cats in the neighborhood or something, or okay. Right. So yeah, will this work on sort of microcomputer or Arduino chip, Raspberry Pi grade stuff? I don't know. I've never literally tried it. I'm not much of the microcomputer fan independently. So I don't know that I can speak very intelligently on this. Scikit-Learn does not, or Scikit-Learn does not tend to be very sort of resource and memory heavy, other than sort of what it needs to be. But the other side of that, I don't know, because it's using things like NumPy and SciPy and things that, when they're installed, can really benefit from being highly configured with your BLOS system, with your binary linear algebra system that's on the actual, way down in the like sub-assembly level stuff of your board. I don't know how well that stuff plays in those microcomputers. I mean, I would guess it's fine because it's on version 0.19. It's been around long enough that there were several versions out when the $1,000 computer was more powerful than the Arduino is now. So I would guess you might need to back off a few, but I would try it and see, and my guess would be it would work just fine. Yeah.
You don't wait for results for a long time?
Oh no, you don't wait for results for a long. I mean, you put massive amounts of data into it, then you will. But no, it's so highly optimized to run things using things like NumPy and SciPy that it's going to do all of its numerical optimization down at like the C and assembly level and the BLOS level, the binary linear algebra level, where the Python aspect of it, the Python runtime aspect of it's a glorified control panel. So if it's going to bog down, it was going to bog down no matter what, even if you build it from dead scratch in C anyway. So, yeah. Is that it? Out of sight, out of mind?
Sounds like it.
That'll work. Thank you.